Get ready for a deep dive into the world of graph theory. Specifically cut problems on graphs.
With multi-edges and loops.
Oh, it's going to get complex.
Yeah.
But trust me.
It's worth it.
So
what's really intriguing is that we're looking at 3 specific problems.
Okay.
Multi-graph matching cut, multi-graph decut, and partially reflexive stable cut.
Got it.
Think of it like strategically slicing a network, but the rules change depending on the type of cut you're aiming for. And here's the real kicker. These problems sometimes behave completely differently when we forbid multiple subgraphs compared to just forbidding one.
Interesting.
It's a bit like adding a new ingredient to a recipe and ending up with something totally unexpected.
I like that.
Exactly. So to understand
these nuances, we need to make sure we're all on the same page.
Of course.
With some terminology.
Okay, let's start with the basics. Okay.
What exactly are multigraphs?
So in a standard graph, you have nodes connected by edges. A multigraph allows multiple edges between the same 2 nodes.
So is that like...
Think of it like having several roads connecting the same 2 cities.
Makes sense.
Yeah.
And what about partially reflexive graphs?
It's simpler than it sounds.
Okay.
A partially reflexive graph is just a graph where some nodes have loops, edges that connect a node back to itself.
Got it.
You could visualize it as a city with some roads that circle back to the same point.
Also like a roundabout in a city.
Okay, got it.
Got it.
The paper also mentions subcubic graphs and edge subdivision.
Right.
Can you break those down for us?
Please.
A subcubic graph has a restriction on its connections. Each node can have at most 3 connections to other nodes.
Got it.
Like a city with a maximum of 3 roads leading out. Edge subdivision. Is a bit like adding a pit stop on one of those roads. You split an edge by adding a new vertex in the middle.
Okay, that makes sense.
Interesting.
Now, before we dive into the problems themselves, the paper mentions this C123 framework for classifying the complexity of graph problems. What's that all about?
The C123 framework, developed back in 2022, provides a systematic way to analyze the difficulty of graph problems when we restrict ourselves to graphs that don't contain specific subgraphs. These are often called forbidding subgraphs.
So it's a way to categorize problems.
Exactly, based on how they behave when certain structures are off limits.
Got it.
The framework relies on 3 core properties, C1, C2, and C3.
Got it.
To classify these problems.
So let's unpack those properties. What does each one tell us about a problem's complexity?
C1 checks. If the problem becomes easy to solve when dealing with graphs that have bounded tree width, you can think of tree width as a measure of how tree-like a graph is. Low tree width means it branches out simply, like a family tree. High tree width implies more complex connections.
Got it.
Like a social network.
So C1 essentially tells us if the problem becomes more manageable?
Precisely. When the graph resembles a tree structure,
got it.
C2 focuses on subcubic graphs. Those with at most 3 connections per node. It asks if the problem remains difficult. Even with this limitation on connections.
So even with that constraint.
Exactly. Some problems remain tough nuts to crack.
I believe it.
Finally, we have C3, which examines whether a problem stays difficult, even after applying edge subdivision to those subcubic graphs.
So it's like asking.
It's like asking. Does adding those pit stops make the problem any easier?
Got it. So C3 explores whether the problem's complexity is tied to the length of individual edges or the overall structure of the graph.
Exactly.
Now, the interesting twist here is that the C123 framework was initially designed with a single forbidden subgraph in mind. Our deep dive today explores what happens when we have multiple forbidden subgraphs.
That's where the real intrigue lies.
Things get a bit wilder, right?
But before we dive into the specifics of each problem, let's remember that easy in this context usually means a problem solvable in polynomial time, and hard generally refers to NP-complete problems.
Right. A quick refresher. Polynomial time means we can solve the problem relatively quickly, even as the graph grows larger. NP-complete problems, on the other hand, lack any known efficient algorithms. for large graphs.
Good.
With that groundwork laid.
Yeah.
Let's tackle the first problem.
Okay.
Multigraph matching cut.
All right.
What's the core question this problem asks?
The multigraph matching cut problem asks, can you divide a multigraph into two parts so that the edges crossing the division form a matching?
I need a quick reminder.
Okay.
What exactly defines a matching in a graph?
A matching is a set of edges where no two edges share a common node.
Okay.
Imagine dividing a network into two teams.
Yeah.
But each person on one team can only have one direct connection to someone on the other team.
Got it.
That's a matching.
So it's like a one-on-one partnership between the two sides.
Yes.
And what does the paper tell us about the complexity of finding this multigraph matching cut?
Surprisingly, multigraph matching cut behaves like a classic C123 problem.
Okay.
Even when we forbid multiple subgraphs.
Wow.
It sticks to the rules.
So even with multiple forbidden subgraphs thrown in, the C123 framework still holds up.
Yeah.
That's unexpected.
How did the researchers prove this?
Yeah, how did they prove this?
The proof has several key parts.
Okay.
First, they demonstrated that multigraph matching cut is solvable in polynomial time if the graph has bounded tree width.
So if the graph is tree-like enough.
Exactly. Finding those matching cuts becomes relatively straightforward.
Got it.
They then showed that multigraph matching cut becomes NP-complete when dealing with subcubic graphs, fulfilling the C2 property.
So even with a constraint of at most 3 connections per node, the problem becomes significantly harder.
And the proof cleverly uses a variation of the classic Boolean satisfiability problem.
SAT.
SAT.
I remember that one.
To demonstrate this NP completeness.
SAT.
Yeah.
It's all about determining if there's a way to assign truth values, true or false, to variables to satisfy a given logical formula.
Okay.
Which variation of SAT did they use for this proof?
They used a variant called 2-3 SAT, where each clause has at most 2 literals, and every variable appears in at most 3 clauses. They map each variable in each clause to specific structures in the graph. For each variable, 6 the dollars, they create a variable gadget, $5, which is a cycle of length 4 dollars. Where pales is the number of occurrences of $6 in the formula. They replace every second edge of this cycle with 2 parallel edges for each clause $6. They create a clause gadget, $6, which is a path of length 2.
Got it.
The idea of the reduction is that for every variable $6, the vertices of the variable gadget, $5, are partitioned by a solution into 2 sets of equal size, one corresponding to the assignment of true to $6, and the other corresponding to the assignment of false to $6.
Got it.
Then for each clause, the 2 vertices of its clause gadget, $60 are assigned to different parts. If and only if the clause is satisfied by the truth assignment.
That's a clever way to represent a logical formula within the structure of a graph. And this construction proves that finding a multi-graph matching cut in this specific type of graph is as hard as solving a 2-3 SAT problem.
Precisely.
Which we know is NP-complete.
But the researchers didn't stop there.
Oh, really?
They went further and proved that multigraph matching cut remains NP-complete.
Wow.
Even when we subdivide the edges of those subcubic graphs.
So even adding pit stops?
This confirms the C3 property.
Doesn't simplify the problem.
You've got it.
That's a strong indication that the complexity is rooted in the graph's overall structure rather than the length of individual edges.
The researchers subdivided each edge of the graph obtained from the instance of 2-3 SAT times for an appropriate value of $2 to get a new graph. And they proved that the original graph has a multi-graph matching cut. If and only if the new graph has a multi-graph matching cut. This shows that subdividing edges doesn't make the problem any easier, as the NP completeness still holds.
It's fascinating how this seemingly simple operation of edge subdivision.
Indeed. Doesn't affect the problem's core complexity.
And it highlights that the arrangement of nodes and their connections plays a more significant role than the distances between them. in determining the difficulty of finding a multigraph matching cut.
Exactly. So despite dealing with the added complexity of multigraphs, we see that multigraph matching cut behaves predictably within the C123 framework.
Right.
Now, are you ready to explore its close relative?
That's the multigraph D-cut.
How does multigraph D-cut build upon the concepts we've just discussed?
Multigraph D-cut generalizes the matching cut problem.
Okay.
Instead of limiting each node to just one connection across the cut, we now allow each node to have at most indie connections to the other side.
So instead of one-to-one partnerships,
great analogy.
we now have teams with multiple connections between them, like a network of collaborators with varying levels of involvement.
And just like its simpler counterpart,
Okay.
multigraph D-cut turns out to be a well-behaved C123 problem.
No surprises there then.
Even when we forbid multiple subgraphs.
But I'm curious about the proof.
Okay.
Does it follow a similar structure to the multigraph matching cut proof?
The outline of the proof closely mirrors the matching cut proof, emphasizing the strong connection between the two problems. To prove that multigraph D-cut is NP complete, when we forbid multiple subgraphs.
We use a variant of SA called NAE3SA.
NAE3SA?
Yes.
Can you refresh our memory on what makes this version of SAT special?
NAE3SA stands for not all equal 3 SAT.
Okay.
It adds a constraint where every clause in the formula, which is a group of 3 variables connected by logical operators, must have at least one variable assigned true and at least one assigned false.
So you can't have all variables in a clause with the same truth value.
You can't have all variables in a clause with the same truth value.
Got it. It's like a requirement for a balanced discussion with differing viewpoints.
I like that analogy.
Okay.
So how do they incorporate NAE3SAT into the multigraph D-cut problem?
The researchers use a similar approach to the previous proof.
Okay.
They map variables and clauses of the NAE3SAT formula to specific structures within the graph. For every variable, $6. They create a variable gadget, $5, which is a cycle of length 6 tebel. Where PP is the number of occurrences of $6 in the formula. The edges of this cycle are partitioned into p-by paths of length 6 that we call variable paths.
Got it.
The key property of the construction is that every variable path is partitioned by a solution into 2 parts. One of size 2 and one of size 4. So that exactly p-to-1 edges connect the 2 parts. For each clause, they create a clause gadget, P2I$, which is a single vertex. Then for each clause, its vertex, ED$, is made adjacent to D later vertices of distinct variable gadgets, corresponding to the variables that form the clause, in such a way that each variable path contains at most one of these vertices.
This sounds very intricate. How does this mapping demonstrate that solving multigraph D-cut on these graphs is as hard as solving NAE3SAT?
The brilliance lies in the way the graph is constructed.
The existence of a multigraph D-cut in this graph directly corresponds to a satisfying assignment for the NAE3SAT formula.
So if we can find a way to split the graph into 2 parts, respecting the D-connections rule, it means we've also found a way to assign truth values to the variables.
And vice versa.
That satisfy the NAE3SAT formula.
If a solution exists for the NAE3SAT instance, a corresponding multigraph D-cut can be found in the graph.
So they've essentially translated a logical problem into a graph problem.
Precisely.
Proving that solving one is equivalent to solving the other.
By mapping NAE3SAT to multigraph D-cut, they've shown that multigraph D-cut is at least as hard as NAE3SAT.
Got it.
Which we already know is NP complete.
It's a clever way to piggyback on the known complexity of NAE3SAT.
Indeed.
To establish the complexity of multigraph D-cut.
And this proof also covers the case of multiple forbidden subgraphs. They show that even when certain subgraphs are forbidden, the problem remains as complex as NAE3SAT.
So far, we've seen that both multigraph matching cut and multigraph D-cut, even with the added layer of multiple forbidden subgraphs, still adhere to the C123 framework.
Yes.
But our third problem, partially reflexive stable cut.
You could say that.
Is where things get a bit more rebellious, isn't it?
This partially reflexive stable cut is where the C123 framework starts to show its limitations.
Were you ready to delve into this more unruly problem?
Are you?
Absolutely. Bring on the challenge.
Okay.
Let's start with a refresher on what a stable cut entails.
A stable cut, also known as an independent set, is a way of cutting the graph. So that no two nodes on opposite sides of the cut are directly connected.
So it's about creating a clean division with no direct links across the boundary.
Imagine you're dividing a social network. But you want to ensure that no one on one side is friends with anyone on the other side.
Right.
It's a stable cut.
And in partially reflexive stable cut,
precisely,
we're specifically dealing with graphs that allow loops.
Yes.
Those edges that connect a node back to itself.
And the paper makes a surprising discovery about this problem's behavior.
Tell me more.
Within the C123 framework.
What makes partially reflexive stable cut?
Here's the intriguing part.
So different from the previous two problems.
When only one subgraph is forbidden, partially reflexive stable cut acts like a well-behaved C123 problem. But as soon as we start forbidding sets of subgraphs containing both pendant subdivisions of nets
we can unpack those terms.
And pendant subdivisions of the H1 graph.
Let's start with nets. What do those look like?
Visualize a triangle with each corner having a single tail, a path extending outwards.
Got it.
That's our basic net graph. A pendant subdivision of a net means taking one of those tails and subdividing it, adding more vertices along the way.
So it's like extending one of the roads.
It's like extending one of the roads.
Leading out of our triangular city.
Leading out of our triangular city.
Got it. And what about the H1 graph?
Picture a square with two opposite corners, each having a single tail extending outward.
Got it.
That's your H1 graph.
And
as with nets, a pendant subdivision of H1 involves subdividing one of those tails, like adding more towns along one of the roads leading out of our square city.
So it's this specific combination of pendant subdivisions of nets.
That's the million-dollar question.
And H1 graphs that throws a wrench into the C123 framework.
And the paper delves into the complexities of this scenario.
What makes this combination so disruptive?
They prove that partially reflexive stable cut is NP-complete. For specific sets of forbidden subgraphs, particularly those containing the C3 graph.
Hold on, H21.
A simple triangle.
Another variation on the H1 graph.
And a slightly modified H1 graph called H21.
I am visualizing it. So forbidding the combination of C3.
It's essentially an H1 graph.
And this modified H21 graph.
Where all four pendant edges.
Makes finding a partially reflexive stable cut significantly harder.
Those tails have been subdivided once. Imagine adding one extra town along each of the roads leading out of our square city.
It sounds like they're building a graph that mirrors the logic.
That's a great way to put it.
Of the NAE3 SAT formula. But with the added constraints of these specific forbidden subgraphs.
And by proving that finding a partially reflexive stable cut in this specific type of graph is as hard as solving NAE3 SAT. They've shown that this problem doesn't always conform to the C123 framework.
This is where things start to get really interesting.
It highlights the limitations.
The C123 framework, which held up so well for the previous two problems.
Of even the most well-structured frameworks.
What breaks down in the face of this specific combination of forbidden subgraphs?
When dealing with the complexities of graph theory.
So are there any scenarios?
There are.
Where partially reflexive stable cut becomes more manageable?
The paper doesn't just focus on the hard cases.
Even with these forbidden subgraphs in play.
It also explores situations.
So there's still glimmers of hope.
Where partially reflexive stable cut becomes solvable in polynomial time.
For finding efficient solutions.
They call these upper bounds.
What are some of those cases?
For the problem's complexity.
Where the problem becomes more tractable.
One interesting scenario involves forbidding both the H1 graph and specific types of net subdivisions, like the RN1-111 graph.
The net with multiple layers sharing a common triangle?
Remember, the RN1-111 graph is essentially multiple layers of net graphs sharing a common triangle.
Like a multi-level net structure.
Exactly. The paper shows that forbidding both H1 and RN1-111 makes partially reflexive stable cut solvable in polynomial time.
Interesting.
So
those forbidden subgraphs can sometimes work together to simplify the problem.
What's the intuition behind this simplification?
Yeah, what's the intuition?
The proof relies on an observation about the number of irreflexive vertices in these graphs. Those without loops.
Right.
They show that if a graph is Rn1, 1R1, 1 free, it can only have a limited number.
So by restricting the presence of this particular type of net subdivision,
precisely,
we also limit the number of vertices they can be without loops.
This limited number of irreflexive vertices allows us to systematically check all possible combinations of these vertices to see if any form a stable cut. Since the number of combinations is limited, we can do this efficiently.
It's like narrowing down the search space significantly.
That's a great way to think about it.
By eliminating a vast number of possibilities.
And this technique highlights the power
of using forbidden subgraphs to constrain the structure of the graph. And in turn, simplify the problem.
It seems counterintuitive that forbidding certain structures,
it might seem that way,
can actually make a problem easier to solve.
But remember, constraints can sometimes bring clarity and order.
Right.
In this case, the forbidden subgraphs impose a structure that limits the number of possibilities we need to consider.
So it's not just about what's absent,
precisely,
but also about how the remaining elements are arranged.
The interplay
that determines the problem's complexity.
Between forbidden structures and the overall arrangement of elements is a recurring theme in graph theory.
Right.
And understanding this interplay
makes sense.
Is crucial for developing efficient algorithms.
Now, the paper also discusses another case where partially reflexive stable cut becomes solvable in polynomial time.
This case,
when we forbid both H1,
involves those net graphs and a different type of net subdivision called N11 del,
where two tails are subdivided once.
I remember that visualization.
And the third tail is subdivided L times.
And forbidding this particular type of net subdivision,
think of it like our triangular city,
along with H1, with two short roads,
also makes the problem more manageable,
and one very long road leading out.
Exactly.
But the proof for this case must be different, right?
You're right.
We can't rely on the same argument.
This time,
about the limited number of irreflexive vertices.
They take a different approach.
What's their strategy here?
Instead of focusing on the number of irreflexive vertices, they delve into the structural properties of these H1 and N111L free graphs.
So they're again dissecting the graph's architecture.
Precisely.
To understand why this specific combination leads to a more tractable problem.
They demonstrate that these graphs can be broken down into smaller, simpler components.
What are these smaller components they break the graph into?
Making the problem easier to analyze.
Yeah, what are those components?
They carefully analyze the relationships between triangles' paths and those degree 2 vertices connected to the triangles.
Got it.
By understanding how these elements interact within the constraints imposed by the forbidden subgraphs, they develop an efficient algorithm for solving partially reflexive stable cut in this specific case.
It's remarkable how they leverage the constraints imposed by the forbidden subgraphs to dissect the graph and reveal its underlying structure.
The power of structural analysis in solving graph problems.
Right.
Sometimes breaking down a problem into smaller, more manageable pieces is the key to finding an efficient solution.
This deep dive has already revealed so many layers of complexity and nuance.
Indeed.
I'm eager to see what other insights we uncover as we continue to explore partially reflexive stable cut. It's amazing how the landscape of partially reflexive stable cut shifts so dramatically, depending on which subgraphs we forbid. It's like exploring a new terrain where the rules of the game can change unexpectedly.
And to navigate this complex terrain, the paper introduces a powerful tool in the form of lemmas.
Lemmas are like those handy shortcuts on a map, guiding us through the intricate paths of a problem.
Statements that help us simplify and analyze these graphs systematically.
What are some of the key lemmas that the paper highlights in relation to partially reflexive stable cut?
One of the crucial lemmas provides a set of properties that allow us to reduce any instance of partially reflexive stable cut.
So like cleaning up the graph and getting rid of unnecessary elements without losing any essential information.
The lemma outlines 4 properties we can achieve through a series of vertex deletions.
Can you walk us through those 4 properties?
Which means we're not fundamentally altering the graph's structure, but rather streamlining it.
I'm curious to see how they help us declutter the graph.
The first property states that we can transform the graph so that every vertex of degree 2, meaning it has 2 connections, becomes reflexive.
So we're getting rid of any dead ends in the graph.
Additionally, we can eliminate any vertices with degree 1.
And ensuring that all degree 2 vertices have those loops connecting back to themselves.
Exactly.
Right.
It's about eliminating unnecessary complexity.
Got it.
The second property tells us we can eliminate any degree 2 vertex that's part of a triangle.
So we're simplifying those triangular structures within the graph.
Precisely.
By removing any degree 2 vertices embedded in them.
The third property focuses on twin vertices. Vertices that share the same set of neighbors. It states that we can safely remove one of these twin vertices.
So if 2 vertices are essentially indistinguishable in terms of their connections,
exactly,
you can streamline the graph by eliminating one of them.
The fourth property deals with situations where one vertex's neighbors are a subset of another vertex's neighbors. In such cases, the vertex with the smaller set of neighbors must be reflexive, and the other vertex must not.
Interesting. So we're, again, imposing constraints on the presence or absence of loops.
Precisely.
Based on the neighborhood relationships between vertices.
And the beauty of these 4 properties
what's so beautiful about them
is that we can achieve them through vertex deletions, which ensures that any simple graph contained as a subgraph in the simplified instance is also present in the original graph.
So we're not just simplifying the visual representation.
Exactly.
But also preserving the essential structural relationships within the graph.
These reductions are like distilling a complex problem down to its essence, making it easier to analyze and solve.
Now, the paper also mentions a lemma, specifically for H1 subgraph-free instances of partially reflexive stable cut. What additional insights does this lemma offer?
This lemma introduces 3 more properties labeled H5, H6, and H7.
Got it.
That allow us to further simplify H1-free graphs.
More tools for refining our graphs.
Let's break them down.
Let's break them down. What does property H5 tell us?
Property H5 focuses on irreflexive vertices, those without loops. It states that in an H1-free graph, every irreflexive vertex must be part of a triangle. That includes another irreflexive vertex.
Though if a vertex doesn't have a loop,
precisely,
it's guaranteed to be part of a triangular structure with at least one other loopless companion.
Property H6 deals with the relationships between triangles within the graph. It tells us that no 2 triangles can share a vertex.
So each triangle is essentially an isolated unit.
Exactly.
It's connected from other triangles.
And finally, property H7 imposes constraints on those isolated triangles. It states that each vertex of a triangle can have only one neighbor outside the triangle. And that neighbor must have degree 2.
So each triangle has 3 arms extending outward.
A vivid description.
And each arm can only connect to a single degree 2 vertex.
And as with the previous lemma, these 3 properties can also be achieved through vertex deletions, preserving any simple subgraphs within the simplified instance.
So again, we're not distorting the fundamental structure.
Precisely.
But rather highlighting its essential elements.
These lemmas provide a framework for systematically simplifying these graphs without losing crucial information.
Now, armed with these lemmas,
the
paper dives into specific cases where partially reflexive stable cut becomes solvable in polynomial time. Can you walk us through one of these upper bound cases?
Of course, one case involves graphs that are both H1 free and RN1111 free.
Right. The net with multiple layers sharing a common triangle.
Remember RN1111 is that multi-layered net structure we discussed earlier? Exactly.
By forbidding both H1 and this specific type of net subdivision.
By forbidding both H1
the researchers demonstrate
and this specific type of net subdivision
that partially reflexive stable cut.
The researchers demonstrate that partially reflexive stable cut
becomes solvable in polynomial time. So those forbidden subgraphs, which initially seem to complicate things, can sometimes work together to simplify the problem.
How do they prove this?
The
proof leverages the simplification techniques we've discussed, particularly the lemmas that allow us to streamline the graph.
Okay.
By applying these lemmas, we can reduce the graph to a simpler form, making it easier to find the solution.
It's like they've created a set of rules for decluttering the problem, allowing us to see the solution more clearly.
And this approach highlights the power of structural analysis and simplification techniques in tackling complex graph problems.
Now, the paper also explores another polynomial time solvable case. Involving graphs that are free of both H1.
That's the net structure.
And a different type of net subdivision called N11L.
With 2 short tails and 1 very long one, the paper proves...
But the proof for this case must be different, right?
Yeah, right.
We can't rely on the same argument about the limited number of irreflexive vertices.
This time, they take a different approach.
Okay, what's their approach?
Instead of focusing on the number of irreflexive vertices, they delve into the structural properties.
So they're again dissecting the graph's architecture.
Precisely.
To understand why this specific combination leads to a more manageable problem.
They show that these graphs can be broken down into smaller, more manageable components.
What are these smaller components they break the graph into?
Which simplifies the analysis.
Yeah, what are they?
They carefully examine the relationships between triangles, paths, and the degree 2 vertices connected to those triangles. By understanding how these elements interact within the constraints imposed by the forbidden subgraphs, they develop an efficient algorithm for finding the solution.
It's fascinating how they leverage the forbidden subgraphs as a guide.
Indeed.
For dissecting the graph and revealing its underlying structure.
It's a testament to the power of combining structural analysis with an understanding of constraints to solve complex problems.
Now, before we wrap up,
Okay.
the paper mentions one more case.
Of course.
Where partially reflexive stable cut becomes polynomial time solvable.
The final case involves forbidding both C3.
Can you tell us about that?
The simple triangle.
H2 has 2 has and 1 1.
And a slightly more complex structure called H2 has 2 have 2 have A2 1 1.
That sounds like another variation on the H1 graph theme we've encountered before.
You're right.
Okay.
It's essentially an H1 graph. Where 3 of the tails have been subdivided twice.
Okay, I'm visualizing it.
Picture our square city.
And forbidding this specific combination of C3.
With 3 of its roads extended by 2 additional towns.
And H2 to 82 through 1101 also leads to a more manageable, partially reflexive stable cut problem.
Exactly.
Another victory for efficiency.
The paper demonstrates that for graphs with these forbidden subgraphs.
But I'm guessing the proof for this case involves some new tricks.
Yes.
What's the key insight that unlocks the solution here?
The researchers introduce a powerful new tool.
A new lemma. I'm intrigued.
A lemma?
What does this property entail?
That allows us to transform any instance of partially reflexive stable cut into an equivalent instance with a very specific property.
So we're guaranteeing that these highly connected subgraphs...
The lemma states that we can transform the graph.
Will always have at least 3 bridges.
So that any connected subgraph...
Connecting them to the rest of the graph.
With a maximum degree of at least 3, meaning at least 1 vertex in the subgraph. Has 3 or more connections. Must have at least 3 vertices that connect to vertices outside the subgraph.
I'm eager to see how this lemma comes into play.
That's a great way to visualize it.
Can you walk us through the steps of the proof?
And this seemingly simple property turns out to be incredibly useful for analyzing partially reflexive stable cut on C3 and H2 201 free graphs.
So they're using a combination of known techniques and this new insight to crack the case.
The proof begins by applying the simplification lemmas we discussed earlier.
Okay.
Those rules for streamlining the graph and eliminating unnecessary elements.
Yeah.
Then they leverage this new lemma, the one about those 3 bridges for highly connected subgraphs, to analyze the specific case of C3 and H2 231 free graphs.
So the forbidden subgraphs are working together to create a very specific landscape.
They focus their attention on the set of irreflexive vertices.
For those irreflexive vertices.
In the simplified graph. Since C3 is forbidden, we know there can't be any triangles with all 3 vertices being irreflexive. And because H2 to 1 2 and 1 1 is also forbidden, the structure of the graph becomes even more constrained.
So the only way to split the graph while maintaining that no direct connections rule
by using these constraints
is to remove all those irreflexive vertices.
And the property guaranteed by the new lemma
Okay.
They're able to prove that the set of irreflexive vertices in the simplified graph must form a stable set.
A stable set meaning no two irreflexive vertices can be directly connected.
Precisely.
Okay.
This is the pivotal discovery that leads to the solution.
Yeah.
If the set of irreflexive vertices forms a stable set, then the only way to create a partially reflexive stable cut in the graph is if this set of irreflexive vertices also forms a cut set.
Got it.
A set of vertices that, if removed, would disconnect the graph.
And since we've already simplified the graph, finding this cut set of irreflexive vertices becomes a straightforward task.
We simply check if removing them disconnects the graph.
Okay.
If it does, we have our partially reflexive stable cut.
Got it.
If not, we know such a cut doesn't exist.
This deep dive has been an incredible journey through the intricacies of graph theory cut problems.
It's been a pleasure to unravel these complexities with you.
We've explored how these problems behave in unexpected ways.
This paper truly pushes the boundaries of our understanding.
When we introduce multiple forbidden subgraphs,
highlighting the intricate interplay between graph structure,
challenging our assumptions about complexity and structure,
forbidden subgraphs, and computational complexity.
And even though some of these problems can be incredibly challenging,
absolutely,
we've also seen that careful analysis.
It's a reminder that even in the face of complexity,
clever techniques,
there's always room for elegant and insightful solutions.
And a bit of ingenuity can lead to efficient solutions.
As we wrap up, what are some of the key takeaways our listeners should keep in mind?
Yes, what are some of those takeaways?
First, the C123 framework, while incredibly useful, is not a universal solution.
Right. We saw how partially reflexive stable cut
it has limitations.
Can behave unexpectedly in those scenarios.
Particularly when dealing with multiple forbidden subgraphs.
Second, forbidding subgraphs can sometimes simplify problems.
Forbidding subgraphs.
But it can also introduce new layers of complexity.
Can sometimes simplify problems.
It all depends on the specific subgraphs.
But it can also introduce new layers of complexity.
And how they interact with the overall structure of the graph.
It all depends on the specific subgraphs and how they interact.
It's like a delicate balancing act.
With the overall structure of the graph.
Constraints can bring order.
Exactly.
But they can also create new challenges.
Finally, and perhaps most importantly. The power of structural analysis and simplification techniques cannot be overstated.
Those lemmas, which might seem like abstract mathematical tools, prove to be crucial for breaking down complex problems.
Exactly.
And revealing pathways to efficient solutions.
And I believe this deep dive has equipped our listeners.
They were our guiding lights in the sometimes bewildering world.
With a newfound appreciation for the beauty
of graph theory cut problems.
Depth and sometimes unpredictable nature of these problems.
So keep exploring. Keep questioning.
Absolutely.
And keep diving deep into the fascinating world of graph theory. All right, let's dive into the world of graphs, specifically cut problems, and how things get really interesting when we start forbidding certain subgraphs. We've got this paper, that's a bit of a head spinner, that looks at how restricting certain structures can completely change the complexity of these problems.
Yeah, it's like we're adding a new set of rules to this mathematical game. We have to solve these cut problems, but with some pieces missing.
Exactly. And what's fascinating is that this paper focuses on 3 specific cut problems. They are multigraph matching cut, multigraph D-cut, and then this one, partially reflexive stable cut, which seems to have a mind of its own.
Oh, you're definitely right to single out partially reflexive stable cut. It really throws a wrench into things, doesn't want to follow the usual patterns.
Okay, so before we get into the complexities, can you remind us what a cut problem is in the context of graphs? It's essentially about dividing a graph into 2 parts, right?
Yeah. Think of it like you have a network, any kind of network, social, computer, whatever, and you want to split it into 2 distinct groups.
Got it. So what makes each of these problems, multigraph matching cut, multigraph D-cut, and partially reflexive stable cut, unique?
Okay, let's start with multigraph matching cut. We're dealing with multigraphs here, which means you can have multiple edges connecting the same 2 nodes. The goal is to find a cut where the edges crossing that cut, the ones going from one group to the other, form a matching. So each node on one side can only connect to, at most, one node on the other.
So it's like a very structured and balanced division, no tangled connections across the cut.
Exactly. Now imagine we relax that matching requirement a bit. That's where multigraph decut comes in. Instead of just one connection per node across the cut, we allow up to connections, like giving ourselves some flexibility in how we make that division.
Okay, I'm with you so far. So where does our rebellious, partially reflexive stable cut fit into all of this? What makes it so different?
All right, this one gets a bit more interesting. We're now working with partially reflexive graphs, meaning we can have loops. That means edges that connect a node back to itself.
Okay, so a node can have a relationship with itself.
Yeah. And in partially reflexive stable cut, the goal is to find a cut where the nodes directly involved in the cut, we call that the cut set, form an independent set. No connections within the cut set itself.
Ah, so they can have connections to nodes on the other side of the cut, but not among themselves. Like we're isolating them in a way.
Yeah, that's a good way to think about it. And what makes this problem so tricky, or rather rebellious as we're calling it, is that it doesn't quite fit into this neat framework for classifying the complexity of graph problems. It's called the C123 framework.
Oh, the C123 framework. Yeah, I remember that from our previous deep dives. Can you give us a quick refresher on how it works?
Absolutely. C123 is like our tool for figuring out how hard or easy a graph problem is when we forbid certain subgraphs. It's got 3 conditions that a problem needs to meet.
Okay, let's unpack those conditions. What's the first one?
So condition C1 says that the problem should be easy to solve, computationally speaking, for graphs with bounded tree width. Tree width is essentially a measure of how tree-like a graph is. The lower the tree width, the more tree-like it is, and, well, usually easier to deal with.
So if a problem checks off C1, it means we have a good chance of finding efficient solutions, at least for certain types of graphs. What about C2?
All right, C2 throws a bit of a curveball. It says that the problem needs to be hard to solve for subcubic graphs. These are graphs where each node has at most 3 connections.
So even if the connections are limited, the problem can still get computationally messy.
Yep. And then we have C3. This one's all about edge subdivisions. Imagine taking an edge in a graph and splitting it into multiple edges by adding new nodes along the way. C3 says the problem should stay hard even when we subdivide edges like this in subcubic graphs.
Ah, so even stretching it out doesn't make it any easier. A tough nut to crack. So if a problem satisfies all 3 of these C123 conditions, then what?
Then we can often predict how hard the problem is based on which subgraphs we forbid. It's like a guide to understanding the problem's behavior.
But you mentioned partially reflexive stable cut doesn't play by these C123 rules. What's going on there?
Well, they found this really interesting case where forbidding specific subgraphs actually makes partially reflexive stable cut super easy to solve. And that shouldn't happen according to C123. For example, if we forbid both C3, which is just a triangle, and H1, which is a graph structure with a central node, and 4 pendant edges.
Wait, so forbidding these simple structures makes the problem easier. That's kind of counterintuitive.
Right. It goes against our usual expectations, and it suggests there's something more going on beneath the surface that we need to figure out.
This is getting interesting. Okay, so how did they even find this out? What methods did they use?
They took a very systematic approach, looking at each of the 3 cut problems and how they behave when you forbid different subgraphs. For multigraph matching cut, they used this clever technique called reduction.
Reduction. Could you unpack that a little?
Sure. They basically took a known NP-complete problem called NAE3SIT. Stands for Not All Equal 3 Satisfiability. It's a logic problem with variables that can be true or false and clauses that combine those variables. The goal is to find a truth assignment that satisfies all the clauses.
Ah, so it's like a logic puzzle with specific rules.
Exactly. They ingeniously transformed this NAE3SIT problem into an instance of the multigraph matching cut problem. Map variables to paths in the graph and clauses to specific structures with triangles and double edges.
So you converted a logic puzzle into a graph problem. I see where this is going.
The cool thing is that the answer stays the same. If you can solve the NAE3SAT problem, you can find a matching cut in the graph and vice versa. This means multigraph matching cut is at least as hard as NAE3SAT, which is already a tough problem.
Okay, so they established that multigraph matching cut is a tricky one. But how does that relate to the C123 framework?
They painstakingly showed that multigraph matching cut satisfies all 3 C123 conditions.
Can we dive into those arguments a bit? Let's start with C1. The one about bounded tree width.
Right. For C1, they used a known result about a simpler problem called simple matching cut. This problem can be expressed in a certain type of logic, and problems in that logic are known to be solvable efficiently on graphs with bounded tree width.
So they linked it to a problem that already behaves well under bounded tree width.
Exactly. And they showed how to transform a multigraph into a simple graph without changing the matching cut properties. So multigraph matching cut also behaves well under bounded tree width, satisfying C1.
Nice. What about C2 and C3, the ones dealing with subcubic graphs and those edge subdivisions?
Well, for those, they use this technique called k-subdivision. Imagine taking an edge and replacing it with a path of length k. They basically showed you can make a k-subdivision of their multigraph matching cut construction, one that's still subcubic, and it keeps the connection to the NAE3 SAT problem.
So even if you make the graph more stretched out, the problem's difficulty stays the same. They nail down C2 and C3.
Exactly. Now, the arguments for multigraph D-cut are pretty similar because it shares a lot of properties with multigraph matching cut. They could adapt a lot of the techniques for matching cut to show that multigraph D-cut also neatly fits into C123.
So 2 down, 1 to go. Multigraph matching cut and multigraph D-cut both follow the C123 rules. But we still have partially reflexive stable cut to deal with. It's the rebel of the bunch. Where does it deviate from the framework?
You remember that surprising case where forbidding C3 in H1 makes the problem unexpectedly easy? That's where things get really interesting. To understand why this happens, we need to look at some specific graph structures.
Okay, I'm ready for more graph theory adventures. Let's do it.
All right, let's start with something called pendant subdivisions of nets. Nets are graphs formed by 3 paths that share endpoints. Now, a pendant subdivision is when we take those paths and extend them outward by adding more edges.
So we're basically adding branches to these paths.
Exactly, and the researchers proved some important lemmas. One of them says that partially reflexive stable cut is solvable efficiently in what we call polynomial time for graphs that forbid both H1, the one with the central node, and 4 pendant edges and any pendant subdivision of a net.
Polynomial time. That's great. It means we have a good algorithm for it. Why does forbidding those specific structures make it so much easier?
The key is realizing that those forbidden subgraphs put a limit on the number of irreflexive vertices in the graph. Irreflexive means no loops. And remember, in partially reflexive stable cut, the cut set has to be an independent set. Loop vertices can never be in that set because the loop creates a connection within the cut set.
Oh, I see. The loops mess things up.
Okay.
So by limiting the number of irreflexive vertices, we're kind of narrowing down the possibilities for stable cuts, making the problem easier to handle.
You got it. And this is just the start. They found even more specific cases where partially reflexive stable cut becomes easy. They looked at this particular type of pendant subdivision of a net called an N11 error L. You get this by taking a triangle and adding paths of lengths 1, 1, and L to its vertices.
Okay, so it's a very specific arrangement of paths extending from a triangle.
Right. And they found that forbidding both H1 and this N11 doll structure also leads to an efficient solution. It's like a precise recipe for taming this problem.
This is highlighting how sensitive partially reflexive stable cut is to which subgraphs we forbid. Even small changes make a big difference.
Yeah, it's pretty remarkable. Now, we need to bring in one more important graph. This one's called H2A2A11. It kind of marks a boundary between the easy and hard instances of this problem.
Okay, H2A111. What's so special about this one? How does it relate to the others?
Imagine you take H1, the one with the central node and 4 pendant edges, and subdivide 3 of those pendant edges. That's how you get H2A211.
Ah, so it's a slightly more complex version of H1.
Exactly. What they found is that forbidding both H2L11 and C3, remember, that's just a triangle, makes partially reflexive stable cut solvable in polynomial time.
Wow. This is incredible. They're pinpointing specific subgraphs that dictate how hard this problem is. It's like a detective story.
It really is. It shows how powerful, careful mathematical analysis can be. But, this is just the beginning. There's even more to uncover about this rebellious problem.
Well, my mind is already buzzing with all of this. I think we need a break to process all this graph theory before we continue.
I agree. Let's take a moment to digest this and come back for part 2. Welcome back. Ready to dive deeper into partially reflexive stable cut. This problem really keeps on giving.
I'm ready. It's like we've stumbled onto a mathematical puzzle box with all these hidden compartments. Last time we were talking about how forbidding certain subgraphs can make partially reflexive stable cut surprisingly easy to solve. I'm eager to hear more.
Right. And one of the coolest tools we can use to understand why this happens is the concept of line graphs. Have you played around with those much?
I've encountered them, but they always make me think a bit harder. It's like we're shifting perspectives from nodes to edges.
Exactly. It's a whole new way of looking at things. In a line graph, we essentially turn the edges of the original graph into nodes. So each node in the line graph represents an edge from the original. And then two nodes in the line graph are connected if their corresponding edges in the original graph share a node.
Okay, I'm starting to see it. It's like we're looking at the connections between connections.
Precisely. Now, for simple graphs, the ones without multiple edges between the same nodes or loops, there's this cool relationship between matching cut and stable cut in terms of their line graphs. It says that if the line graph of a simple graph has a stable cut, then the original graph has a matching cut, and the other way around. If a simple graph with a minimum degree of at least 2 has a matching cut, then its line graph has a stable cut.
Wow, so matching cut and stable cut are linked through this line graph idea. They're like two sides of the same coin.
That's a great way to put it. And what's really neat is that this paper explores how this connection extends to multigraphs and partially reflexive graphs.
Okay, now we're bringing those multi-edges and loops back into the picture. Things are about to get more complex. How does the line graph idea handle those extra features?
Well, they use a slightly modified version of a line graph. They denote it as LG, and it's derived from the line graph of the underlying simple graph of a multigraph G. But here's the key difference. LG adds a self-loop to every node that corresponds to an edge with multiplicity at least 2 in the original multigraph G.
So the line graph is basically keeping track of those multi-edges by adding loops.
You got it. It's like a way of remembering that information from the original graph. And with this modified line graph, they can show a connection between multigraph matching cut and partially reflexive stable cut. They prove that if this LG has a partially reflexive stable cut, then the original multigraph G has a multigraph matching cut. And the reverse is also true. If G contains a multigraph matching cut and every node has at least 2 edges connected to it, then LG contains a partially reflexive stable cut.
That's amazing. So even with those more complex graphs, matching cut and stable cut are still connected through this line graph perspective.
It really is. It shows how these different graph problems are related in these really deep ways. Now, it's interesting to note that the researchers could have actually used this connection to derive similar results about the complexity of partially reflexive stable cut.
So they had a different path they could have taken.
Right, but they chose a different route, a more direct and, I'd say, elegant one for the specific results they were after. It's like taking the scenic route sometimes.
I love that. It reminds us that in math, there are often multiple ways to solve a problem. And sometimes the most direct path isn't always the most interesting. You know, something else you mentioned earlier was that the authors use a weaker version of condition C3 for partially reflexive stable cut. Do you remember? C3 was about those edge subdivisions.
Oh, yeah, that was interesting. Remember, C3 says that the problem needs to remain hard even when we subdivide edges of subcubic graphs in any way possible. But for partially reflexive stable cut, they only needed to worry about subdividing edges where one of the endpoints is a looped vertex. And all the new vertices we add in the subdivision, those also have to be looped.
It's a more specific type of subdivision. So why was that enough? Why focus on those looped vertices?
It all goes back to what a stable cut means in partially reflexive graphs. A stable cut needs the cut set to be an independent set, which means no connections within the cut set itself. Looped vertices can't be in a stable cut set because the loop creates a connection within the cut set. It breaks the rules.
Ah, that makes sense. The loop ruins the independent set requirement. So subdividing edges between two unlooped vertices wouldn't really change the potential stable cuts. The subdivisions that matter are those that involve looped vertices because they could lead to new stable cut sets.
That's it. By focusing on those specific subdivisions, the researchers were zeroing in on the situations where things could actually get more complicated.
It's about using the right tool for the job. Now, what about those upper bounds they talked about? They had these lemmas showing when partially reflexive stable cut becomes polynomial time solvable, meaning we have a good algorithm for it. Do any of those stand out?
Yeah, they had some really cool results. Remember those lemmas about pendant subdivisions of nets? The ones showing that forbidding certain structures makes the problem easier.
Yes. One of them said that partially reflexive stable cut is polynomial time solvable for graphs that forbid both H1 the graph with one central node and 4 pendant edges and any pendant subdivision of a net.
That's right. And the proof of that relied on showing that you can limit the number of irreflexive vertices, which basically limits the possible stable cuts. It's like shrinking the search space.
Makes sense. And there was another lemma that explored a specific type of pendant subdivision of the net called N11 That's the one we get from a triangle with paths of length 1, 1, LL. attached to its vertices.
Exactly. And forbidding both H1 and this N111L structure also makes the problem efficiently solvable. It's pretty wild how those very specific structures play such a big role in the problem's complexity.
It's all about the subtle details. It really shows the connection between the structure of a graph and how difficult it is to solve problems on that graph.
You got it. And this is just the tip of the iceberg. There are even more intricate lemmas and theorems that dig deeper into partially reflexive stable cut. It really shows the creativity involved in this type of math research.
I'm also really struck by how this research shows the beauty and complexity hidden within something as seemingly simple as cutting a graph into parts.
I agree. It's fascinating. It's like we're looking at a tiny world under a microscope. Is there anything else from these lemmas or our line graph discussion that you'd like to go back to? Anything still puzzling you?
Well, one thing I've been thinking about is lemma 7. I remember it was about transforming an instance of partially reflexive stable cut into an equivalent one with some nice properties. Do you think we could unpack that a little more? How does it fit into the bigger picture?
Absolutely. Lemma 7 is a key step in proving one of the main theorems about partially reflexive stable cut. It essentially says that for any constant Cray, we can take an instance of the problem and transform it into one where any connected subgraph with K or fewer vertices and a maximum degree of at least 3 must have at least 3 vertices that have neighbors outside of that subgraph.
Okay, that's a lot to unpack. What does that mean in simpler terms?
Imagine we have a small, densely connected group of nodes within a bigger graph. Lemma 7 says we can change the graph so that this group has at least 3 connections to nodes outside of the group. It's like making sure these small groups are well integrated into the larger graph.
Ah, I see. So we're avoiding situations where these small groups are isolated or only connected through a single point.
Exactly. We're ensuring good connectivity. And this property is crucial for proving Theorem 7, which says that partially reflexive stable cut is polynomial time solvable for graphs that forbid both H2A, 2L11, and C3.
Right. That was one of the main results about when this problem becomes easy to solve. But how does lemma 7 help with that proof?
Well, the proof of Theorem 7 relies on showing that after applying the reduction from lemma 7, the set of all irreflexive vertices, the ones without loops, actually form a stable set.
And a stable set means no 2 vertices within the set are connected.
You got it. So if we can prove that the set of irreflexive vertices is a stable set, and we can also show that removing this set disconnects the graph, meaning it forms a cut set, then we've found a partially reflexive stable cut.
That makes sense. So lemma 7 helps to make the structure of possible stable cuts simpler.
Precisely. It's all about setting things up for a more elegant solution.
This whole conversation about partially reflexive stable cut has been so insightful. It's amazing how tiny changes to the rules can completely change how hard the problem is.
I agree. And this study really shows how important frameworks like C123 are for understanding how hard computational problems are. But, as we've seen, there are always exceptions, always problems that challenge our expectations.
It's like we have a map for this mathematical world, but there are still uncharted territories out there.
Absolutely. And that's what makes it so exciting. Ready for the final part of our deep dive?
Lead the way. I can't wait to see what else we discover. Okay, we're back, ready to wrap up this incredible journey into the world of cut problems. Partially reflexive stable cut, it really threw us for a loop, but in a good way.
Yeah, it definitely keeps things interesting. So many layers to peel back. It seems like every time we think we've got a handle on it, there's a new surprise waiting.
Before we finish up, I want to go back to the proof of Theorem 7 for a bit. We talked about it briefly, but I think it deserves more attention. It's the one that proves partially reflexive stable cut is polynomial time solvable, meaning we have a good algorithm for it, when we forbid both H2, 22411, and C3, right?
Yes, that's the one. If you recall, the proof used lemma 7 to reduce the graph to a simpler form, making it easier to find a solution.
Right, and they focused on the set S, which contains all the irreflexive vertices, the ones without loops. But I'm still a bit hazy on why proving that S is a stable set was so crucial for solving the problem.
It all comes down to simplifying things. Remember, a stable cut needs the cut set to be an independent set, meaning no connections within the set itself. If we can prove S is a stable set, meaning no 2 vertices in S are connected, then finding a partially reflexive stable cut becomes much easier. If S is a stable set, A and D removing S disconnects the graph, then boom, we've found a partially reflexive stable cut. It's a shortcut to the solution.
Oh, now it's clicking into place. So proving that S is a stable set is like laying the groundwork for a much cleaner, more efficient solution.
Yeah.
But how did they actually prove it? What was their strategy?
Well, they used a proof by contradiction. They started by assuming that S is not a stable set, just to see where that would lead them.
So they intentionally introduced a bit of chaos into the system, like shaking up a puzzle box to see what falls out.
Exactly. If S isn't a stable set, there must be two adjacent irreflexive vertices. Let's call them P and Q.
Okay, so we're assuming S is a bit messy and seeing if that leads to any problems, like a detective looking for clues at a crime scene.
Exactly. Now, because we've applied the reduction from lemma 7, and both P and Q have a degree of at least 3, there must be distinct vertices A and B that are neighbors of P, and distinct vertices C and D that are neighbors of Q. We'll call this set of 6 vertices D.
Okay, so we have this small cluster of vertices around P and Q. I'm picturing it. It's like a little neighborhood in our graph.
Right. And lemma 7 tells us that there must be at least 3 vertices within the set D that have neighbors outside of D. And these neighbors outside of D must be distinct.
Why is it important that those neighbors outside of D are distinct? What's the significance of that?
Well, think about it. If they weren't distinct, it would mean we'd have a pair of vertices that act like gateways, meaning all paths between D and the rest of the graph would have to pass through them. This would contradict lemma 7, which guaranteed good connectivity between small clusters and the rest of the graph.
I see. We don't want to create bottlenecks. We need those connections to be spread out to maintain that good connectivity. It's like having multiple exits in case of an emergency.
Exactly. So the researchers examined all the possible scenarios based on which vertices in D have neighbors outside of D. And because the graph is H2, 2, 2, 1, 1 free, and C3 free, they could systematically rule out each scenario. Every single one led to a contradiction.
So they were like detectives meticulously eliminating suspects, one by one. They cornered the culprit by process of elimination.
Precisely. By carefully going through all the options, they showed that the initial assumption that S is not a stable set couldn't possibly be true.
It's like a mathematical magic trick. They made our initial assumption disappear. So they proved S is indeed a stable set. And since checking whether S is a cut set is pretty straightforward, they nailed down that partially reflexive stable cut can be solved efficiently for those specific graphs.
Exactly. They untangled this web of cases and constraints to find exactly when this problem becomes solvable with a good algorithm. It's like they found the secret combination to unlock the puzzle box.
This whole deep dive into partially reflexive stable cut has been a wild ride. We've learned so much about how sensitive the complexity of a problem can be to the specific subgraphs we forbid. It's amazing how small changes can make such a huge difference.
I completely agree, and it really highlights how important these frameworks like C123 are for understanding the world of computational complexity. They give us tools to analyze and classify problems, but like we've seen, there are always exceptions to the rules, always problems that push us to think outside the box.
It's like we have a roadmap, but there's still uncharted territories out there waiting to be explored. It's both humbling and exciting to realize how much more there is to discover in the world of graph theory and computational complexity.
You said it. This deep dive has just scratched the surface. If you're interested in learning more, definitely check out the full paper for all the details and proofs. It's a fascinating read.
Well, we've reached the end of our deep dive, but the journey of exploration continues. Keep those minds curious, keep asking questions, and never stop exploring the fascinating world of mathematics. Until next time, happy problem solving.
Welcome to another deep dive. Today, we're going to be exploring the world of cut problems on graphs, specifically the ones that allow for multi-edges and loops. We've got some excerpts here from a research paper. It's called A Forbidden Subgraph Study for Cut Problems on Graphs Permitting Loops and Multi-Edges. And looks like we're going to be talking about some interesting complexity classifications.
Yeah, this paper really digs deep into how allowing multi-edges and loops can really just change the whole complexity landscape of these cut problems.
Yeah, before we get into the specifics, I'm kind of curious about the C123 framework the paper uses. I kind of have a general idea of what it's for, but could you break it down for me?
Absolutely. The C123 framework is basically a way to classify the complexity, the computational complexity of certain graph problems, particularly when we're dealing with graphs that forbid specific subgraphs. So it helps us determine whether a problem is likely to be hard, meaning like NP-complete, or easy, meaning solvable in polynomial time. And this classification hinges on whether the problem meets 3 criteria, C1, C2, and C3.
Okay, so C1, C2, C3. It's like a checklist. Can you walk me through what each of these criteria actually means in the context of graph problems?
Sure. So C1 means that the problem is solvable in polynomial time. For graphs with bounded tree width is like a measure of how tree-like a graph is. So the lower the tree width, the more it resembles a tree structure.
Okay, so if a problem can be solved efficiently on graphs that are like very tree-like, then it gets a check mark for C1. What about C2?
C2 means that the problem becomes NP-complete when we're dealing with subcubic graphs. These are graphs where each vertex has at most 3 neighbors.
Okay, so if a problem becomes really hard to solve when we're dealing with those subcubic graphs, it passes the C2 test. What's C3?
So C3 focuses on what happens when we subdivide edges in subcubic graphs. So subdividing essentially means replacing a single edge with a path of multiple edges. If the problem remains NP-complete even after we subdivide edges in subcubic graphs, it satisfies C3.
So just to sum it up, if a problem is easy on tree-like graphs C1, hard on subcubic graphs C2, and stays hard even when we subdivide edges in those subcubic graphs C3, we can confidently call it a C123 problem.
Exactly. And this categorization really helps us to understand the problem's complexity in more general cases, especially when you start forbidding certain subgraphs.
Yeah, that's super helpful. Now let's dive into the cut problems that this paper tackles. I see they focus on multigraph matching cut, multigraph D-cut, and partially reflexive stable cut. Before we get lost in the details, can you remind me what a cut is in the context of a graph?
Sure. Imagine you want to partition the vertices of a graph into 2 distinct groups. A cut is basically the set of edges that you'd have to cut to separate those groups.
Okay, so a cut is all about dividing a graph into 2 separate pieces. How do these 3 types of cuts differ from each other?
So a multigraph matching cut is a cut where the edges that are cut form a matching. This means each vertex on one side of the cut can have at most 1 edge, connecting it to a vertex on the other side.
So it's like each vertex can only hold hands with one other vertex across the divide to ensure a clean separation.
Precisely. And then we have a multigraph D-cut, which generalizes this idea. So here, each vertex can have at most D edges crossing the cut. So it's like each vertex has D hands to hold, allowing for more connections across the partition.
So matching cut is just a specific case of D-cut, where D is equal to 1. Got it. Now what about this partially reflexive stable cut? That one sounds a bit more mysterious.
This one is interesting. So in a partially reflexive stable cut, the set of edges forming the cut must be an independent set, meaning no 2 edges in the cut share a common vertex. Additionally, the partially reflexive aspect means our graph can have loops, but those loops cannot be part of the cut.
Okay, so the edges in the cut have to maintain their distance. No direct connections allowed. And any loops in the graph are off limits for cutting. To make this more concrete, can we maybe use a real-world example to illustrate one of these cuts?
Sure. Let's take multigraph matching cut. Imagine you're designing a communication network, and you need to divide it into 2 subnetworks to enhance security and prevent the spread of potential disruptions.
Okay, I see where you're going with this.
You could represent the network devices as vertices in a graph, and you draw edges between devices that communicate with each other. A multigraph matching cut would then represent a division of the network, where each device in one subnetwork can only communicate directly, with at most 1 device in the other subnetwork. So this limits the potential damage from a security breach or a system failure, as it prevents widespread communication between the 2 subnetworks.
That's a really helpful example. It shows how these seemingly abstract mathematical concepts can have very real-world applications. Now that we've laid the groundwork, let's dive into the paper's findings. They start by examining multigraph matching cut. What did they uncover about its behavior within this C123 framework?
They found that multigraph matching cut behaves precisely as you'd expect from a C123 problem. It fits perfectly within the framework's classifications.
So it's a well-behaved problem then. Can you walk us through how the researchers actually proved this alignment with the C123 criteria?
Sure. Their proof involved 2 main steps. First, they showed that multigraph matching cut is solvable in polynomial time for graphs with bounded tree width. So this addresses the C1 criterion. And they achieve this by cleverly transforming the multigraph into a simple graph. For each multi-edge with null edges, they replace it with null or parallel paths of length 2. And then they applied known results for matching cut on simple graphs with bounded tree width.
That's an interesting approach, transforming the problem into a more familiar form. What about the second step?
The second step focused on demonstrating that multigraph matching cut becomes NP-complete when dealing with subcubic graphs and their subdivisions. So this covers the C2 and C3 criteria. And they achieved this through a reduction from the not all equal 3 SAT problem, so NAE3 SAT.
Could you remind me what NAE3 SAT is all about? It's been a while since I've delved into those satisfiability problems.
Certainly. So the NAE3SAT problem asks whether there exists a truth assignment for a given Boolean formula in conjunctive normal form, where each clause has 3 literals, such that each clause has at least one true literal and at least one false literal.
So it's like finding a way to satisfy the formula without having all the literals in a clause agree.
Exactly. The researchers showed that any instance of NAE3SAT can be transformed into an instance of multigraph matching cut on a subcubic graph in such a way that the NAE3SAT instance is satisfiable if and only if the corresponding multigraph matching cut instance has a solution.
So by linking these two problems together, they prove that if multigraph matching cut were easy to solve on subcubic graphs or their subdivisions, then we could also easily solve NAE3SAT, which we know is NP-complete.
Precisely. And this implies that multigraph matching cut must also be NP-complete on subcubic graphs and their subdivisions. So this elegantly addresses the C2 and C3 criteria, confirming that multigraph matching cut indeed falls under the C123 framework.
That's fascinating. Now, moving on to multigraph decut, did they find any surprises there?
Not really. It behaved just like multigraph matching cut, aligning perfectly with the C123 framework.
So it also falls under the C123 umbrella. Can you elaborate on how they demonstrated this?
Sure. So they followed a similar approach as with multigraph matching cut. First, they established its polynomial time solvability on graphs with bounded tree width, so again addressing the C1 criterion. And they tackled this by creating a simple graph, where each multi-edge, with multiplicity at least 2, is replaced with parallel paths between $seps. Then they applied established results for decut on simple graphs with bounded tree width, demonstrating the problem's tractability in this case.
So they tamed the multi-edges, just like before. What about C2 and C3?
For the second part, they once again employed a reduction, this time from the well-known vertex cover problem, to show that multigraph decut becomes NP-complete for subcubic graphs and their subdivision.
Right. Vertex cover is about finding the smallest set of vertices that covers all the edges in a graph. How did they connect this to multigraph decut?
They devised a clever transformation where they took any instance of vertex cover and constructed a corresponding instance of multigraph decut on a subcubic graph. So they mapped vertices in the vertex cover instance to edges in the multigraph decut instance, and they showed that a solution for vertex cover could be directly translated to a solution for multigraph decut, and vice versa.
So they cleverly intertwined these two problems, proving that if multigraph decut were easy on cubic graphs or their subdivisions, we could efficiently solve vertex cover as well, which we know is NP-complete.
Exactly, and this solidifies the fact that multigraph decut is indeed a C123 problem, just like multigraph matching cut.
It seems like these first two problems are playing by the rules, neatly fitting into the C123 framework. This sets us up perfectly for some surprises.
With partially reflexive stable cut, right?
You're absolutely right. Hold on to your hats, because this is where things get really interesting.
I'm ready for the plot twist. How does partially reflexive stable cut throw a wrench into the C123 framework? Well, while partially reflexive stable cut initially seems like a well-behaved C123 problem, when we only forbid one particular subgraph, the situation changes drastically when we forbid multiple subgraphs. Its complexity behavior shifts dramatically, deviating from the typical C123 pattern.
Wait, so it's like this problem has a split personality. When we constrain it with just one forbidden subgraph, it plays nice. But as soon as we introduce more forbidden subgraphs, it goes rogue.
You got it. It really challenges our understanding of these complexity classifications.
This is definitely piquing my curiosity. I'm guessing the paper dives into the proofs behind this unexpected behavior, right?
Absolutely. And things do get a bit technical, but I think we can break it down in a way that makes sense.
I'm all ears. Don't hold back on the details. Our listeners are here for the nitty-gritty.
All right, so they first established that partially reflexive stable cut is NP-complete, even when a single specific subgraph is forbidden, so demonstrating alignment with the C2 and C3 criteria. They do this through a reduction, this time from the 3SAT problem. So they map clauses and variables in the 3SAT instance to specific structures in the constructed graph, and a satisfying assignment for the 3SAT instance corresponds to a valid partially reflexive stable cut in the graph, and vice versa.
So they connect partially reflexive stable cut to the classic 3SAT problem, which we know is NP-complete. But this only addresses C2 and C3. What about C1? Is partially reflexive stable cut solvable in polynomial time for graphs with bounded tree width?
That's the interesting part. It gets more nuanced when we start forbidding more subgraphs. The researchers explore specific classes of graphs that are free of certain combinations of subgraphs, which is where they discovered this divergence from typical C123 behavior.
So this is where the aha moment happens. Things are about to get really exciting. I'm ready to dive into these specific cases and see how partially reflexive stable cut breaks the mold.
Let's do it. Prepare to enter the world of forbidden subgraphs and unexpected complexity twists. Welcome back. Last time we left off with this intriguing discovery that partially reflexive stable cut can act like a C123 problem sometimes, but totally break the rules in other cases. It all comes down to these fascinating combinations of forbidden subgraphs.
Yeah, I'm eager to delve deeper into those specific cases. It's like we're about to uncover a secret code book for understanding the complexities of this problem. So where should we start?
Okay, let's start with one of the instances where partially reflexive stable cut becomes surprisingly tractable. The case of N1 tolls Rn1 subgraph-free graphs. So remember, N1 is that graph with the central vertex connected to three others, each with a pendant edge sticking out. And N11 Rn1 lons are net. Is that triangle with a single edge leg extending from each corner.
Right. And a pendant subdivision of a net means we can stretch out those legs by subdividing the edges.
Right.
And true N dollars, like its sound, means our graph doesn't contain Rno or more disjoint copies of those pendant subdivided nets.
Okay, I'm trying to visualize this. So you're saying that if our graph doesn't have this $1 structure and doesn't have too many of those nets with the stretched out legs, then the problem becomes easier.
Exactly. The researchers proved that partially reflexive stable cut can be solved in polynomial time on these HBO1 Rn1 $1 subgraph-free graphs.
Okay, but why does avoiding these particular subgraphs make the problem more manageable? Like, what's the underlying logic here?
The key here lies in the fact that avoiding H1 and limiting the number of those pendant subdivided nets imposes a constraint on the number of irreflexive vertices in the graph. So remember, irreflexive vertices are those without loops.
Okay, so the absence of these specific structures somehow restricts the number of vertices without loops. But how does that help us solve partially reflexive stable cut more efficiently? Well, to find a partially reflexive stable cut, we need to identify a stable cut. And a stable cut can only consist of irreflexive vertices, because by definition, no two vertices in a stable set can be adjacent, and a loop creates an adjacency between a vertex and itself.
I see. So by limiting the number of potential candidates, for our stable cut, we're essentially reducing the search space.
Exactly. The researchers show that any H1 or Rn1 free graph can have at most 12 R11 irreflexive vertices. So this bounded number of irreflexive vertices is the key to polynomial time solvability. We can simply check every possible subset of these irreflexive vertices to see if it forms a stable cut. And since the number of subsets grows polynomially with the number of vertices, the problem becomes solvable in polynomial time.
That's really clever. So by understanding the structural limitations imposed by these forbidden subgraphs, we can cleverly constrain the problem and find a solution more efficiently. It's like finding a shortcut through a maze.
Precisely. And this really highlights the interplay between graph structure and computational complexity. But wait, there's more. They go on to investigate another class of graphs where partially reflexive stable cut becomes surprisingly well-behaved. H1 and NE11 subgraph-free graphs.
Okay, let's break this down. We're still avoiding $1, but now we're dealing with a slightly different variation of our net. What does NE1 represent?
So any $1 represents a net, where one of those legs extending from the triangle has been stretched out into a path of length $. So a graph that's H dollars, any $1 subgraph free doesn't have H dollar as a subgraph. And it doesn't have any nets, where at least one leg is a path with length $1 or more.
So we're still banning H$1, but now we're also saying no to nets with excessively long legs. And this makes partially reflexive stable cut solvable in polynomial time too. I'm curious to know the reasoning behind this result. It seems counterintuitive that such a specific constraint would lead to such a dramatic change in complexity.
The intuition here is again to limit the number of irreflexive vertices. But the argument gets a bit more intricate this time. So they start by assuming that our graph contains a path of length $2. If it doesn't contain a path of length $2, then the problem essentially boils down to a smaller localized portion of the graph, making it easy to solve.
Okay, so the presence of a path of length $2 to dollars is what makes things interesting. But why? How does that path come into play?
Here's the clever part. They demonstrate that if any triangle in the graph doesn't have a vertex from that path of length $2, then you can actually find a subgraph that looks exactly like an Olivier part, a net with a leg of length the dollars. This contradicts our initial assumption that the graph is HH111 subgraph free.
That makes sense. So forcing every triangle to have at least one vertex on that specific path prevents the formation of those forbidden net structures. But how does this relate to the number of irreflexive vertices?
It all ties together beautifully because the number of triangles in the graph is limited by the length of that path, which is $2 a dollars. The number of irreflexive vertices is also bounded. They demonstrate that the maximum number of irreflexive vertices, in this case, is $60. So once again, we're back to restricting the number of potential candidates for our stable cut. And since we only have a limited number of irreflexive vertices, we can simply test all possible subsets to find a solution in polynomial time.
Exactly. This result really highlights how subtle changes in the allowed subgraph structures can dramatically alter the complexity landscape of a problem.
It's amazing how these seemingly minor tweaks to the rules of the game can have such a profound impact on a problem's solvability. It's like discovering a hidden doorway in a seemingly impenetrable wall, but they delve into even more intricate scenarios, right?
Oh, absolutely. This paper takes us on a deep dive into several other specific graph structures and the surprising complexity results they reveal. Well, I'm ready to keep exploring. Let's see what other hidden patterns and unexpected twists we can uncover in this fascinating world of forbidden subgraphs. Welcome back. We've been on quite a journey with partially reflexive stable cut, exploring how this problem can sometimes adhere to the C123 framework and sometimes totally defy it. It's like we're witnessing a graph theory rebellion unfold right before our eyes.
It's definitely been a wild ride. Last time we saw how forbidding specific subgraph combinations can actually make this seemingly unruly problem solvable in polynomial time, but there's still more to uncover. The paper goes even deeper, meticulously mapping out the boundaries between tractability and intractability for partially reflexive stable cut.
I'm ready for more. It feels like we're about to step into an even more intricate part of the complexity maze. So what's next on our exploration?
Let's talk about H2 and $2 and $2 and $1 in whitejack. A graph that's closely related to H1 but with a little twist. It's like we've taken H1 with its central vertex and 3 legs, and we stretched out 3 of those legs by subdividing them just once.
Okay, let me picture this. So we start with H1, which has that central vertex connected to 3 others, each with a single edge leg. Then we pick 3 of those legs and replace the single edge with a path of 2 edges. There's our H2, $2, $2, $1.
Precisely. Now here's where things get interesting. Partially reflexive stable cut becomes solvable in polynomial time. For graphs that are both H2 and $2 and $2 and 111 subgraph free. Remember, C33 represents a triangle.
Wait, so if our graph avoids both this slightly stretched version of H$, $1 and triangles, then partially reflexive stable cut becomes easy. I'm really curious about the logic behind this. It seems counterintuitive that forbidding those 2 specific structures would have such dramatic impact on complexity.
The proof for this result relies on a clever insight about the structure of these particular graphs. So the researchers first pre-processed the H2, $2, $2, and $2 and 1 self-sub free graph, applying specific rules to simplify its structure, without changing the solution to the partially reflexive stable cut problem.
Okay, can you remind me what those pre-processing rules are all about? Like, what kind of transformations do they apply to the graph?
Sure. The rules ensure that every vertex of degree 2 in the graph is reflexive. In other words, every vertex with exactly 2 neighbors must have a loop. Additionally, they ensure that no degree 2 vertex is part of a triangle, and that the graph has no twin vertices sharing the same set of neighbors.
So they give the graph a little makeover, making sure those degree 2 vertices are well-behaved, and eliminating any redundant structures. But how does this pre-processing help us solve partially reflexive stable cut?
Here's the key insight. In a pre-processed TH2, $200, and $191 to C3 subgraph for free graph, the set of all irreflexive vertices forms a stable set.
Hold on. Let me make sure I'm following you. You're saying that after we apply these pre-processing rules, all the vertices without loops automatically become a stable set, meaning no 2 of them are adjacent. Why is that?
It stems from the specific constraints imposed by the forbidden subgraphs and the pre-processing rules, the absence of H2 and $202 and $1 and $120, and the specific conditions on degree 2 vertices create a situation where any 2 irreflexive vertices cannot be adjacent without creating one of the forbidden structures.
Okay, I'm starting to see the connection. So we've established that all the irreflexive vertices in these pre-processed graphs form a stable set. How does that lead us to a polynomial time solution for partially reflexive stable cut.
Remember to solve partially reflexive stable cut. We're searching for a stable cut, and a stable cut must consist only of irreflexive vertices. Since we now know that all the irreflexive vertices already form a stable set, the only remaining question is whether this set also forms a cut, whether it separates the graph into two disconnected parts.
That makes perfect sense. Yeah. So the preprocessing and the forbidden subgraphs simplify the problem immensely. We no longer have to worry about finding a stable set. It's given to us. All we need to do is check if this stable set also happens to be a cut, which is a much easier task.
Exactly. Checking if a set of vertices forms a cut can be done efficiently. So by demonstrating that the set of irreflexive vertices always forms a stable set in these preprocessed graphs, the researchers essentially reduce partially reflexive stable cut to a simple cut problem, making it solvable in polynomial time.
Wow, that's incredibly elegant. By carefully analyzing the structure imposed by the forbidden subgraphs and applying those clever preprocessing rules, they were able to untangle this seemingly complex problem and reveal a straightforward solution. It really highlights the power of deep structural insights in algorithm design.
I couldn't agree more. And what's especially fascinating is that these findings challenge our initial assumptions about the complexity of partially reflexive stable cut. It seemed like this problem was all over the place, sometimes behaving like a C123 problem, sometimes breaking all the rules. But by delving into the intricate details of specific graph classes, the researchers were able to uncover a hidden order within this apparent chaos.
Yeah, it's like they found a hidden key. That unlocks the secrets of this problem's behavior. It makes you wonder what other graph problems might have these hidden patterns just waiting to be discovered. What other complexity frameworks might we need to rethink?
These are fantastic questions. I think this paper is just the tip of the iceberg. It highlights the importance of going beyond established frameworks, of diving deeper into the subtle nuances of graph structure. Who knows what other surprises are waiting to be uncovered?
This has been an incredible deep dive. We've learned so much about partially reflexive stable cut, its intricate relationship with the C123 framework, and the power of forbidden subgraphs in shaping a problem's computational destiny.
Absolutely. It's a testament to the beauty and depth of graph theory, a field that continues to surprise and inspire.
This exploration has definitely sparked my curiosity. To delve even further into the fascinating world of graph theory, I can't wait to see what other secrets and surprises await us. And to our listeners, thank you for joining us on this deep dive. Keep those graphs connected and those minds curious.